Module 3, Lesson 3, Trees and Traversal Process. For this module, we will be discussing the different types of tree graphs, traversal process for trees, expression tree notations, spanning tree, and minimum spanning tree. What is a tree? A tree basically are models used in computer science, chemistry, geology, botany, psychology, and many other areas. Trees were actually introduced by the mathematician Arthur Cayley in 1857 in his work Counting the Numbers of Isomers of Saturated Hydrocarbons. The two isomers of butane, which are as follows, are eventually designated and drawn in the graph of a tree. Organizations of computer files into directories and subdirectories and files is naturally represented as tree looking like this. Trees are also used to represent structures of organizations like your given organizational chart. By proper definition, a tree is simply a connected undirected graph with no simple circuits. Hence, if a particular graph is undirected, therefore there is no orientation on the edges of your corresponding tree, and it has a unique simple path between any of its two vertices. If we are to ask which of these following graphs are trees, then eventually you would note that the following graphs, this one and this one, are trees, because trees are considered to be acyclic, whereby there are no possible circuits that can be formed on your tree. But if I look at your respective graph, here you could actually form a cycle on this loop. And this particular graph does not provide any connection on this vertex to this set of vertices. Therefore, this particular graph then is not connected. Hence, it's not a tree. Rooted trees. A rooted tree is a tree in which one vertex is designated as a root and every edge is directed away from this corresponding root. These are common illustrations of your corresponding rooted tree. Although vertex A happens to be the root of this given tree, the root may be labeled in different manners, and it may be positioned in different manners too. The terminology for rooted tree is a mix from botany and genealogy. If vertex B of a rooted tree other than the root, then the parent of vertex B is a unique vertex U, such that there is a directed edge from U to V. When U is a parent of V, then V is called the child of U. Vertices with the same parent are referred to as siblings. Ancestors of a vertex are vertices in the path of the root to this vertex, excluding the vertex itself and including the root. The descendants of this vertex V are those vertices that have V as an ancestor. The vertex of a rooted tree with no children is then called a leaf. Vertices that have children are called internal vertices. So given here is one such particular application again of your rooted tree, which is seen on your corresponding family tree. This happens to be the family tree of Nicholas. Traversal process for your trees. Ordered rooted tree are often used to store information. Ordered rooted tree can also be used to represent various types of expressions, such as arithmetic expressions, which involves numbers, variables, and operations. The listings of the vertices of ordered rooted tree used to represent expressions that are useful in evaluation of these expressions. Procedures for systematically visiting every vertex of your rooted tree are then referred to as traversals. So these traversal processes are eventually process that involves visiting each vertex exactly once of your corresponding rooted tree. One such procedure is then called your universal address system, whereby the corresponding procedure for your respective rooted tree starts from your given root and goes down to the lower levels. Hence, the usual procedure when labeling a corresponding rooted tree using the universal address system is that you label the root with an integer value of 0, and its children directly connected to the root are labeled 1 to k from left to right. And then for each corresponding vertex v at a level below your corresponding children, then it's labeled as k dot v notation, which eventually mentions that this particular children are children of this given vertex. Hence, when labeling universal address system, this would be one such example of which. This common labeling system is actually found on given table of contents of your respective textbooks, and you will see that your textbook is grouped into different chapters, and each chapter has its own subchapter, which are labeled 1.1, 1.2, 1.3, etc., etc. Another traversal process is known as the pre-order traversal process. By definition, if you let your graph T be a rooted tree with a corresponding root R, then the pre-order traversal process begins by visiting each of your corresponding vertex, which are subtrees from your R, from left to right on your given tree. The pre-order traversal process begins by visiting one root of your corresponding vertex R, starting from a pre-order process, which usually starts at the left and then goes to your vertices on the right, which is eventually illustrated by this given process. If you then try to establish a pre-order traversal list, it's basically a list of vertices that are visited in a pre-order traversal manner. If you're given particularly, let's say, a rooted tree like this, whereby your given root is A, then in order to create this particular list, you need to list down all the vertices that will be visited, starting from your root, going to other vertices on your given graph. Note that a pre-order traversal process prioritizes vertices on the left. Therefore, in order to generate the root, you go down one level and place all the parent on the left and its children directly on its right. And you keep doing so on every level until all the levels eventually are cleared and included in the list. So if we go down one level, your corresponding vertices, your parent vertex A would now be at the left of its children B, C, and D. Note, B still has children, E and F, D still has children, G, H, and I, and other vertices still have children below them. So if I go down one level again, for parents B and D, we then shift parent B to the left and its children directly on its right, while parent D is shifted on the left and its children G, H, and I are then shifted to its right, directly on its right, thus giving us a corresponding partial list now to be equivalent to this. Note that E still has children, likewise G still has children, and K still has children. E and G eventually has children on the same level. Therefore, if we go down one more level, we then shift parent E, vertex E, to your left, and its children directly on its right, which are J and K. Likewise, we do the same for vertex G, parent G, shift it to the left, and then place its children directly on its right, thus giving us a list now to be equivalent to a partial list equivalent to this. Note that K still has children on the our lowest level. So when we go down one more level, we then complete the list. So we simply shift your vertex K parent to the left and its children directly on its right, giving us a corresponding list now like this. Note that this particular list prioritizes vertices on its left, as seen from your given rooted tree. You start off with your corresponding vertex A, seen on my list, which is here. And if you read the list from left to right, you will notice that it prioritizes vertices on the left. The next vertex would be B, which is directly on its left. The next vertex would be E, which is directly on its left. The next vertex would be J, which is on its left. As soon as all vertices on the left are traversed, you then move to vertex G, to the right, which is in this case vertex K. And then vertex N, O, P, and then vertex F, vertex C, Vertex D, then prioritize verses on the left, G first, then L, and then M, and then finally ending with vertex H and I, as seen on the list. That is how pre-order traversal process is done. The other traversal process is called the in-order traversal process. By definition, an in-order traversal process of your rooted tree consists of your respective root R, and the idea starts, or the process starts with your root I, but eventually it places this time your corresponding verses on either side of your given parent, thus an in-order traversal process eventually works at the leftmost vertex, going onto its parent and placing all other children on the other side. Note that when you do in-order traversal process, you basically subdivide children on either side of the parent. Hence, if we apply that on this given particular traversal tree and evaluate for its traversal list, the in-order traversal list, we then place the children on either side of the parent. In as much as possible, you place equal number of children on either side. However, if children turns out to be odd numbered, therefore children on the right must be greater than the one on the left. Hence, seen on this corresponding tree, we ended up with 3 children directly connected to vertex A, which are vertex B, C, and D. Therefore, if more children are always on its right, that would mean place vertex B on the left and 2 of the children on its right, which are respectively C and D. If there are 5 children connected to your vertex A, then 2 children will go to the left, 3 children will go to the right. If there's only 1 child connected to vertex A, then that child goes to the right of vertex A of the parent. Hence, if we go down one level, we place vertex B on the left of vertex A, and on its right, you have vertices C and D. Note that vertex B still has children, vertex D still has children, vertex E still has children, vertex G, likewise vertex K. So if we go down one more level for vertex B and D, we shift the children to either side of the parent. Therefore, we end up with this partial list now. Note that vertex E still has children, likewise vertex G, and seen here as well as vertex K. So if we go down one level now for the parents E and G, we place their children on either side of this parent, we end up with this partial list. And finally, vertex K still has children, and if we subdivide and place the children on either side of parent K, you'd end up with vertex N on the left and versus O and P to its right, therefore completing your in-order traversal list, which now starts with vertex J, E, N, K, O, P, B, F, A, C, L, G, M, D, H, and I. And the last traversal process, known as the post-order traversal process. A post-order traversal process this time is the exact opposite of your pre-order traversal process, which should mean that if the pre-order traversal process prioritizes verses on its left, therefore the post-order traversal tree prioritizes verses on its right, visiting all verses on its right first and then traversing all other verses on its left. Hence, your corresponding process is now illustrated like this. So the analysis still begins with your root and then visits the rightmost vertex and then proceed on to the left. So if we're given the same rooted tree in order to apply traversal process now, we will apply a technique to generate the list opposite to that of your pre-order traversal process. Since the pre-order traversal process places the parent on the left, if you go down one level, this time, you place the parent on the right and the children are on the left. So if I go down one level as seen on this given rooted tree, the parent A now goes to the right of my corresponding list and children's B, C, and D precedes your vertex A. Hence, it now appears like this. Note that vertex B still has children, vertex D still has children, vertex E still has children connected to it, vertex G, and vertex K. So if I go down again one level for parent B and D, I place the parent to the right, its children on its left. Therefore, we'd end up with a partial list now looking like this. Note that G still has children, E still has children, and K still has children. So we again place the parent on the right and its children directly on its left. Hence, if we go down one more level, we end up with this partial list. And as seen from this partial list, vertex K still has children and O and P. So we place the parent K to the right and its children, J and OP, preceding it on the left. Therefore, we'd end up with a corresponding list now looking like this. And if you do look at the list, it basically prioritizes vertices on the right. However, you would have to read the list starting from right to left, starting with the root vertex A, which is seen on your rooted tree as this. And if you look at the list going from right to left, it prioritizes vertices on the right because after A on the left, it's followed by D, and then I, and then H, and then G, and then M, vertex L, and then C, and then B. Prioritize the one on the right first, which is vertex F, and then E, and then prioritize vertex on the right, which is K, and then P, and then O, N, and finally ending with vertex J. That is how a post-order traversal process is now done. This particular traversal process, as mentioned, the pre-order, the in-order, and the post-orders are the ones that are oftenly used for your expressions and mathematical equations. The prefix notation or polish notation is actually applied if you traverse your corresponding rooted tree using prefix or pre-order traversal process. This particular expression is known as the prefix form. This expression is actually developed by a Polish logician named Jan Lukasiewicz. Using the prefix form notation, you will notice that there is technically no need in order to place braces on your given expression. Thus, your respective expression like this, having a tree for your letter A to look like this, will have a given prefix notation like this. Note that in order to establish your corresponding prefix notation, you need to have an idea on how your expression tree is actually built from your given proposition. Operators eventually precede operands in a prefix form in this given expression. Parentheses therefore are not needed in this particular representation, since it becomes unambiguous. Prefix expressions are evaluated by working from right to left, and when we encounter an operator, we perform the corresponding operation with the two operations to the right, which are the values or children. For example, on this given particular mathematical expression, let's try to determine the prefix notation. So we first create the expression tree for this given expression, and then starting from the root, prioritize versus on its left. Therefore, ending it with a prefix notation equal to this. An infix notation. Basically, an infix notation is an in-order traversal process whereby it produces the original expression with parentheses, showing which particular operands are actually performed first. So hence, given the example A and B having the following expression trees, if you write down the infix notation or the in-order traversal process on how this particular expression trees are traversed, you will see that you will end up with the same exact expression you have on your given expression, and that you need parentheses in order to show priority or hierarchy in terms of your operands. The postfix notation is also called the reverse polish notation. A postfix notation is obtained by applying a post-order traversal process on your given rooted tree. Again, from this given example of our letter A and B having the following expression tree, this time we prioritize vertices on its right starting from the root, so we eventually write down your prefix or postfix notation to be equivalent to this. On that same note, parenthesis here is not needed since parenthesis becomes unambiguous. A binary operator with its two operands eventually follow your corresponding postfix notation or reverse Polish notation, which eventually makes the expression work from left to right, carrying out the operation represented by your operator on its preceding operands. On this given mathematical expression, let's try to determine now the postfix notation for your given expression. As denoted here, this is the expression tree that we eventually got from this given equation, and your postfix notation now looks like this. Interpreters of reverse Polish notation are often stack-based and are used by your microprocessors, even though this particular technique tends to be a bit obsolete for calculators. Modern calculators nowadays makes use of an infix notation whereby you simply type the expression in the manner how you see it on your given equation, making use of parentheses to prioritize which operations should be performed first. However, on microprocessors like the ones used in your computers, still, these techniques are still being applied and employed by your processor to evaluate operations, tasks, process, whether that may be logical, arithmetic, or even a simple operation process that involves memory location or retrieving items in your memory. When operation is applied on your corresponding processor, interpreters of this reverse Polish notation eventually are pushed into place. Operands are pushed into stacks, and when the operation is performed, the operands are eventually popped out of the stack and its result pushed back on the corresponding process. So the value of the postfix notation on your corresponding top of the stack eventually goes down until all the operations are being implemented. This particular advantage makes it very easy to implement your operations in a very fast manner. Let's try to evaluate a prefix notation. Given this particular expression in a prefix notation, you simply start off with operators seen on the rightmost value, which in this case is raised to. And the elements that are subjected to raised to are its children, which are the ones on the right of your operator. So, assuming these are all single-digit numbers, therefore this is interpreted to be 2 raised to 3, which has a value of 8. So replace all three characters with 8, the next operator would be division, and is subjected to its children 8 and 4, which is interpreted to be 8 divided by 4, which would then equal to a result of 2. Then the next operator would be multiplication, applied to its children 2 and 3. When you multiply 2 and 3, you'd end up with a product of 6. So if you replace all three characters with 6, you'd end up now with the next operator, which is subtraction, which turns out to be 6 minus 5, having a difference of 1. And finally, if you replace that with 1, the last operator involved is simply addition, adding the two elements, 1 and 2, giving you a corresponding sum of 3. So the final answer here is 3. If you're given then this corresponding prefix notation, the final answer then would be 8. On this particular prefix notation, if you evaluate then the final value, it results into 27. And on this particular prefix notation, if you evaluate then the final value, you'd result into 4. When we evaluate a postfix notation this time, we prioritize operators that are seen on the left. And in this case, we operate using multiplication first on the children, which are seen on the left, 2 and 3. Assuming these are single-digit numbers, you'd end up with the product of 2 times 3, And if you replace all three characters with the product of 6, you'd end up with the next operator to be the difference between 7 and 6. So you'd have 7 minus 6 with a difference of 1. And if you replace all three characters with 1, the next operator would be raised to. When applied to your given children, you'd end up with 1 raised to 4, which eventually has a corresponding value of 1. And if you replace all three characters with 1, you'd end up with the next operator to be a division applied on its children 9 and 3, interpreted to be 9 divided by 3 with a corresponding quotient of 3. And finally, the last operator would be addition applied on your corresponding children 1 and 3, interpreted to be 1 plus 3, therefore ending up with a sum of 4. Hence, if you're given the corresponding postfix notation to look like this, its final value then would be 40. For a particular postfix notation now, with this given elements, you'd end up with the value 32. And for this particular postfix notation value, you'd end up now with an answer of 30. Spanning tree. In mathematical field of graph theory, a spanning tree basically is a connected undirected graph, having vertices that eventually spans from your every given vertex. Since a tree does not have a loop, therefore no cycles are supposed to be formed on this given span. By definition, a graph G is considered to be a spanning tree if graph G contains subgraphs that contains a tree on its corresponding vertices. A simple graph with a spanning tree must be connected, since there is a path on the spanning tree between any two vertices. On the other hand, every bridge of graph G must belong to your graph T, or to a tree. A spanning tree is then a connected graph, which can also be defined to contain the minimum number of edges that is needed to connect all vertices on your given graph. Hence, if you're given this particular graph, the edges highlighted in blue refer to your spanning tree. Note that it contains the minimum number of edges that are present in your graph to connect every vertex seen on your given graph. Hence, if you're given a graph like this, and if you're asked to determine its spanning tree, you can only make use of edges that are present on this graph and form a corresponding tree that will allow you to connect every vertex seen on this graph. Note, not all edges are eventually used on your given spanning tree. So, you simply remove some edges and determine the minimum number of edges that will be able to interconnect all of these corresponding vertices, starting with the following edges that are removed A and E, A comma E, then you have E comma F, then C comma G, ending up with this corresponding spanning tree containing a minimum of 6 edges that will interconnect all of your 7 vertices. Note that this is not the only possible solution of spanning trees seen on this graph. These are also possible solutions for your given spanning tree on the given graph. Note that each particular spanning tree only contains a minimum of 6 edges in order to interconnect all 7 vertices. And these particular edges must be the ones present on your given graph. A minimum spanning tree. A wide variety of problems are solved by finding a spanning tree on a given particular weighted graph containing the minimum weights of edges in your given tree. A minimum spanning tree is basically a connected weighted graph that has the smallest possible sum of weights on its edges. Hence, if you're given a particular weighted graph that looks like this, in order to determine then the minimum spanning tree, you need to create a spanning tree that will connect every corresponding vertex using a minimum set of edges. Plus, when you sum up all the weights associated to each edge, it should also end up with a minimum sum. Therefore, this is one possible solution, whereby you utilize the edges BF, AB, FG, AE, IJ, FJ, CJ, CD, GH, HL, and KL to form your minimum spanning tree, ending up with your corresponding total weight of 24. Again, you could likewise make use of this solution using this time edges CD, KL, BF, CG ABFJ, BCJK, GHIJ, and AE, again ending up with a minimum sum of 24. A spanning forest. A spanning forest basically is a graph with no cycle, and a spanning forest is a type of subgraph that generalizes the concept of your spanning tree. Therefore, it simply means that it's a particular graph of tree whereby the subgraph, each subgraph of your corresponding spanning forest is also a spanning tree. This ends Module 3, Lesson 3.